After setting a new pro-class World Time Attack lap record at World Time Attack 2018 with a 1 minute 19.8 second lap time, the RP968 Porsche has definitely turned World Time Attack on its head. We decided to get a little bit more involved with exactly what powered this engine, and we're here at PR Technology with Oskar from Elmer Racing, all the way from Finland, the designer and builder of the Thor Billet aluminium engine. So Oskar, for a start, I think we're going to go back a little bit earlier in the week leading up to World Time Attack, and while probably most of the spectators had no idea of the troubles that PR Technology were going through, there were a few issues around the head gasket sealing on the Thor engine. So can you give us a rundown on what caused these issues and why they came up?
Well, I mean, now in hindsight, of course, it's clear what happened, or more or less clear. But then there were a lot of question marks and didn't really know the specs and everything. So I've designed the engine to run a flat gasket, and I mean, I try to know a lot about a lot of things, but there are a lot of things, of course, that I'm not a super good expert on. And so apparently it's quite usual to have steps in the MLS gaskets around the cylinders to concentrate the clamping force there. But I've designed that clamping force into the actual engine block and head design instead. So the MLS gasket the team got for the engine did have a step in it, and the sleeve installation sort of step is not large enough to support that extra clamping force on the actual sleeve. So it's designed to support that from the sleeve and also the aluminum around that sleeve, sort of the actual block material. And so with the extra step there and concentrating the force on the sleeves, that was pushing the sleeves in, because it was okay when you were mounting it, but then at running temperature, the yield strength of the aluminum goes down, and then it reached the sort of critical limit, and the sleeves push down a little bit. And then, of course, when all the bolts and everything are tightened to spec when it's cold, and something moves a little bit, then it's not going to seal anymore. And yeah, they had big issues with that.
So essentially what that does is allow that combustion pressure to make its way out of the combustion chamber where we want to keep it, and it makes its way into the water jacket and pressurizes the water jacket?
Oh yeah, that's correct. I mean, they're a super professional team, so they have a sensor in the coolant system for pressure, and they noticed that, and so they didn't end up breaking any. Typically you see the radiator's balloon or something like that, but they caught that early and they didn't create any further complications with that. So that was one of the things that allowed us to get that fixed. So
I think another point, just while you're talking about that coolant pressure sensor, as you say, it's not a sensor that is that common, but not getting on top of that really quickly as soon as that pressure builds up in the cooling system. If you continue to run the engine under high boost, we also see essentially it torches a path from the combustion chamber or from the cylinder out to the side of the block, so that can actually ruin the deck surface of the block as well as the cylinder head. Now, I just want to touch on a slight difference here between your bespoke engine design, and we do hear a lot of problems where people are fitting aftermarket ductile iron sleeves to a conventional aluminium engine block. Let's say, for example, here Nissan SR20 or maybe Mitsubishi 4B11. So when people get beyond the limits of the factory aluminium block there, it's quite common to fit ductile iron sleeves, and we hear a lot of problems with those dropping. That's more in line with issues around the accuracy of the machinist's ability to fit those sleeves in the first place. But this, just to be clear, is a very different situation, correct?
I would think so. I mean, there really isn't, when you're running an engine, there really shouldn't be any forces pressing down on the sleeve from the actual running. I mean, it's a clamping issue mostly. So, but yeah, I'm not really that familiar with those issues. So yeah, I don't think they're the same thing, but I'm not sure. I would need to be more familiar.
In terms of the sleeves that you've got fitted to this, and really this is one of the areas where this problem was highlighted, you've kind of alluded to it, the width of that flange at the top of the sleeve that locates on the aluminium block is quite thin. So how wide is that where it locates?
We're running dry sleeves in the engine because we want to keep as much as of the real block material as possible, because that increases the rigidity of the block, and that's incredibly important to keeping all the surfaces flat and keeping the the pressures as even as possible, so that, I mean, helps everything live, and everything seals better, and everything is happier. So when we're running the dry sleeves, we want to run those as thin as possible to keep as much aluminum as possible between the cylinders. So the sleeves we're running, well, I mean, I think it's safe to say we're running as thin sleeves as possible, and it's a little bit over 1 millimeter. I won't disclose exactly what the dimensions are, but very, very thin. And then the step at the top, we run that as small as it needs to be, so we can run round sleeves, because that helps with fitting, and there are lots of engine builders that prefer the option of being able to change the sleeves at the track if a piston breaks or something, and you just end up scratching that. So then having a round top is really important, so you can just slam in a new one.
So in other words, those sleeves aren't Siamesed into the neighbouring sleeve?
Yeah, that's correct. So yeah, and that ends up sort of giving you a really thin step at the top to locate the sleeve sort of height-wise. And yeah,
that's where that force acting on what is a very narrow width of that lip is what's dropped the sleeve. So the team had this issue before you actually got to the track, and essentially on Thursday afternoon, the media day before the actual World Time Attack event started, the team were basically at a point where they were ready to pull the pin. I believe they had already gone through the process of having the deck surface of the block machined flat again, had run it again with a new gasket, and exactly the same problem had happened. It had forced those sleeves down. So what was your solution to this issue?
Yeah. It was, of course, team stuff, and I don't know everything, and I'm like the guru that arrives and says how everything should be done, and it works like that. But I mean, I at least like to think that I had a major influence on that. But yeah, so we looked through the sort of event, like how things have led up to this, and I sort of concluded, okay, I mean, it's reasonable to expect that this is what's causing it, that there is actually a step in the MLS gasket. It wasn't clear to me before that, even if there was a step or not. And then I did some very, very quick calculations. I realized, okay, I mean, there's no way that tiny step on the sleeve is going to be strong enough to hold for the head stud clamping forces. So yeah, we looked at the dimensions and how thick that step is and how much the sleeves have pushed down, and all the sleeves have pushed down an equal amount. So we were looking around at, okay, I mean, I thought it should be good. I mean, just put in a new head gasket, put the head back on, don't do any decking at all, and it should be good to go, because that was like closer to what I've designed it to do. But it was, I mean, really touch and go. I think Rod that sent a message, I mean, the owner and a great guy that does the whole team. So yeah, he sent a message over on Thursday before we got to the track, like, yeah, we had a problem again, and we needed to pull the head gasket, and we're not going to be able to run. And yeah, got there and looked at the things, and okay, maybe it's not so bad. But yeah, I was giving it maybe 75%, 80% chance, trying to estimate conservatively, like if it will be good or not. And Rod he said, yeah, he was maybe 50-50 that we will be able to do one lap.
Sounds like you should maybe be a betting man, because obviously history has shown that it did work and it did hold together. So I think that the point I'll just make there as well is the conventional wisdom when a sleeve has dropped, which I've sort of alluded to there. It is a common problem in the aftermarket with OE factory blocks that have been modified. The conventional wisdom would be to do exactly what the team did, to deck the block so everything's flat again. But as you've said there, with the thickness of that lip and the strength of the aluminium material supporting it, of course, that was just going to continue to push that sleeve lower, and you're going to go through exactly the same problem. So at least you got on top of that and got a solution. It was probably great for PR Technology and the owner that you did turn up there. Now, I just want to go back to those sleeves there, because you've sort of alluded to the thickness there. While we don't have an exact number, around about 1 millimeter. For the sort of specific power levels that this engine is capable of, you said around 1,500 horsepower in a circuit race application. To me, that sounds like a very thin sleeve. So where is the trade-off between, you've said you want to keep maximum aluminium between the sleeves for strength, but where's your trade-off between keeping the aluminium for strength and sacrificing some of the thickness of the ductile iron sleeve or liner?
Well, we basically want to run the sleeves, I mean, basically only as a coating, so as thin as possible. The thinner we can make it, the better for the engine, but you don't want to make it so thin that you start cracking it and losing pieces, because then it's going to have a bad day, of course.
So in conventional factory engines that are aluminium, we've seen over the last few years a lot of manufacturers have now ditched liners and are using a coating on the aluminium directly so that the rings will not wear the soft aluminium. Is that an option, or is that really not suited? You've just not got enough strength in the raw aluminium at these sort of power levels?
Well, the aluminum alloy we use is around twice as strong as the aluminum alloy typically used for blocks. So I mean, it's very, very strong. The only reason we're running sleeves is basically a Nicosil coating would be the ideal solution, but the only reason we're not doing that is because we don't have any test results for that yet. And I don't feel comfortable testing stuff on customer engines unless they specifically request that. And it's a very, very performance sort of critical thing. And on this type of engine, it's the sort of getting the last 2 or 3 horsepower isn't that important when they were running around 1,000 kilowatts this weekend, and they hadn't had it turned up yet to 11 yet. So,
I guess the other aspect there, if you run that Nicosil coating or a similar coating on the bore, it removes that ability to replace an individual liner if you've had a problem. And let's be honest, even with the best of intentions, the best of everything, when you're running engines at this sort of power level, things can and do go wrong. So the ability to fix a problem like that without scrapping an entire expensive billet aluminium block is obviously essential. There's one other aspect I just wanted to talk about here with these billet aluminium blocks. They have come through and become more popular, but we've seen them sort of really come out more from the drag racing world initially, and now we're starting to see them become adopted more and more for circuit racing. And there's a very big difference between what will work for a drag application where the car is only under high load for maybe 6 or 7 seconds, and then obviously you're talking about a circuit car that needs to be under high load for a minute 20, minute 30 in a row. The area I'm looking at here or interested in is the thermal expansion of the aluminium. It's obviously a lot higher than a cast iron block. So does this cause you any issues when you are choosing suitable bearing clearances, particularly for the main bearings?
Yeah, that is a major aspect to look into, and that of course needs to be taken into consideration, like what the power levels are and how much flex are you expecting in the crankshaft, because I mean it's nice and straight when you have it on the table, but when it's running in the engine and you're really pushing it as hard as it can be pushed, it moves around by a significant amount. So you need to have enough clearance there so that you're not going to like start cutting the edges on the bearings. And beside that, you need to get enough mass flow through the bearing gaps to cool the bearings also. But in practice, you want to run a really small gap at room temperature because the expansion rate, because the crankshaft is an iron-based alloy that has a much lower thermal expansion rate than the block that is aluminum. So at around the same temperatures, the hole is going to get much larger than the pin inside it. So your bearing increase, or the clearances are going to increase quite significantly. So
I think there's a general trend when you're building performance engines to go with a clearance that is slightly looser than what would work for a factory engine for exactly the reason you're saying. Obviously, everything does tend to flex and move at very high specific power and RPM levels, but of course it is that trade-off as well. As those clearances get bigger, you also tend to lose oil pressure too. So sort of where's the trade-off on those two factors? Is oil pressure a problem? Have you seen issues with that with aluminium blocks as well?
Well, with the oil pressure, you only really need enough oil pressure to get the oil to the locations you need it to be. Then it's just a question of mass flow, basically. And one of the main things, you need to get the oil to the connecting rod pin, basically, from the main bearing. And depending on the type of drilling, you see a lot of OEM styles and a lot of aftermarket cranks also that have just through drilled mains, basically. So you need to have enough oil pressure to push the oil all the way into the center of the crankshaft before it starts making its way out to the connecting rod bearing. And that's something that we've addressed. We have a sort of I think it's cross drilling. I'm not really sure what the correct term for that is, but we have angle drillings that go to connect those together, and that are specifically angled and modified to not create high stress locations for that, but that helps a lot to sort of minimize the required oil pressure for that. Of course, then you end up having the oil squirters, which if you need to cool the pistons on the way up also to get more cooling capacity, then you again need to run quite a high oil pressure to get enough exit velocity from the nozzles. But there are lots of things that need to be taken into consideration with that.
Of course, I guess you've got a little bit more flexibility around oil flow and oil pressure when you're using a dry sump system over a conventional oil pump.
Yeah, that is. I mean, you can afford to squirt a lot of oil around all over the place, basically, and not have big issues with that. And yeah, I mean, you can scavenge the oil so efficiently without. I mean, especially with a complete custom engine that is built specifically to be dry sumped, then you can have sort of low locations where you suck out the oil from, and you can dimension all the holes correctly to not have any backflow into the crankcase. And yeah, it helps a lot.
You've just also mentioned under piston oil squirter, so I just want to dig into that a little bit because particularly with modified factory engines used for circuit racing, there are two schools of thought on the under piston oil squirters. One is that they aid lubrication and also cooling the underside of the piston. But the other school of thought is that they take needed oil away from the bearings because obviously some volume of oil will be lost to those under piston oil squirters. The fact that you're using them in the Thor engine obviously suggests that you are a believer, but can you give us some insight into your thoughts around them, pros and potentially cons?
Well, we're running a really large piston. We're at 116 millimeters, and the sort of thermal conductivity scales very poorly with the diameter, because when you increase the diameter, the surface area increases quicker than that, and then you have sort of less area to transfer the heat away from the piston. So the larger the piston you have, the more cooling you need on the underside, and that increases that. But we're also running piston-guided connecting rods, and that needs extra oil also for the guiding surfaces at the top of the piston. So that's also a huge requirement. And of course, when you're doing a custom engine, you just need to dimension the parts to be able to flow enough oil to make that happen.
Let's just go back to that piston-guided con rods. Can you give us a little bit more explanation around what exactly that means and why you've done that?
Okay, yeah. So when you have the connecting rod, basically you have just a cylinder at the bottom and a cylinder at the top that locates those. So it will like go out the end of the engine. Of course, you need some surface at some point to like limit that movement. And there are, of course, two ways to do that. You can do that either from the top or from the bottom, and traditionally that's been done from the big end at the crankshaft end. But then you end up needing a lip on the crankshaft to do that, and then that lip also needs a counterbalance on the other side of the crankshaft. And with the piston-guided option, we've probably been able to pull maybe a kilo or something off of the crankshaft with that. So I think it's a very good option.
It makes a lot of sense. So essentially what you've got there is tight clearances between the pin end of your connecting rod and the pin boss in the piston, and that's what locates the connecting rod?
Yeah.
All right, look, it's been some interesting insight there, Oskar, finding out about those problems, because as I say, not everyone knows, but of course, when you're trying to develop an engine at this level, unfortunately, things can go wrong that were outside of your specification list, and it's great that you guys managed to work through it and get a solution and a lap record. And we hope that the car's back next year, because my understanding is that it wasn't running full power. There were still some developments that were being worked through with the car to improve its performance. So it's the second fastest car currently around Eastern Creek, and it's being beaten only by an open-wheeler A1 GP car. So we look forward to seeing if that car can actually become the fastest car ever around Eastern Creek. Thanks for the chat, Oskar.
Excellent, thank you.
If you like that video, make sure you give it a thumbs up, and if you're not already a subscriber, make sure you're subscribed. We release a new video every week. And if you like free stuff, we've got a great deal for you. Click the link in the description to claim your free spot to our next live lesson.